All right, so in today's lesson, I want to talk to you about a concept called molecular polarity or molecule polarity. So far what we've looked at is, we've looked at the type of bond that might form between atoms that are in a covalent bond. So for instance, here I can see that there's, a covalent bond right here, and there's another covalent bond right here. And so although the bond between A and B over here, those might be polar covalent bonds. So maybe this right here is a polar covalent bond, and then same for the other atom. It doesn't necessarily mean that that molecule as a whole is a polar molecule. So today we're going to talk about how that can be and why that is. So you'll remember that a couple of days ago we assigned a certain atom within a covalent bond as being slightly negative or slightly positive. So let's just envision that we have a case here where B is the more electronegative of the two atoms that are there. So B is more electronegative than A. So because of that, B is going to be pulling the electrons closer to it, and therefore those electrons will be spending more time around B, and so therefore B adopts what we would call a slightly, let me do that again, a slightly negative charge. And as a result, I think I'm just going to blow this up a little bit. There, we can see that a little bit better now. So we would give B a slightly negative charge. And as a result, our A would have a slightly positive charge. But what about the second B over to the left? Well, it would also adopt a slightly negative charge. So really, the electrons are not spending as much time around A as they are around the two atoms that are connected to A, right? So this creates a bit of a pull. And those of you that were in physics will understand what a vector is, and I'll leave it to you to explain it to our current chemistry students who are not in physics. But essentially, a vector is a line that has direction, that is of a certain size or magnitude that implies a certain direction. So we could describe direction, the direction of your movement in meters if you're, walking somewhere. But we could also describe the direction of the electron pull. In this particular case, we would draw a dipole vector. Okay, so di meaning two atoms and pole meaning the polarity. So I can draw a dipole vector from A towards B, and I draw that arrow pointing in the direction of the more electronegative atom. Now, to indicate that A is the slightly positive atom in the bond, we would add a little plus sign to it. And so I can also draw a dipole vector going from A towards the second B atom that would be of equal magnitude, equal size, assuming that the electronegativity difference between A and B is the same for both B atoms. And we can see here that those vectors are in opposite direction but equal size. And so, for instance, let's think about this as if we were walking somewhere. So if I walked, let's say, 2 steps forward and then 2 steps back, I would be in the same place that I started. So the overall dipole vector summation would be 0. So -2 plus 2 would give me an overall pull of 0. So that's a great example of how I might have a polar covalent bond, but my overall molecule would have 0 polarity because the poles are acting in different directions. So let's describe that even further. So we would say that we're going to consider the electronegativity differences as vectors. We're going to draw them in from the positive pole in the direction of the negative pole. And we're going to see if those vectors, those dipole vectors, when we add them up, if they don't cancel, then we say that the molecule has an overall dipole and that it is a polar molecule. However, if we see that the vectors do cancel, like in the above example, we would say that the molecule has no net dipole and it is therefore considered to be nonpolar. All right, so at this point, I would like to go through a couple of examples with you. So the first thing that you need to do is you need to really be given the structure, or you need to create the structure of a particular molecule. And so your textbook will provide you with some homework questions, and you may not know what the three-dimensional structure is of that compound. And so I want you to feel free to go ahead and Google its Lewis structure so you get an idea about what its 3D orientation is. Because determining its 3D orientation is not a skill that we learn in grade 11. It's a skill that we learn in grade 12, interestingly enough. So I'm going to go ahead and draw the Lewis structure for this. So I know that chlorine has 7 electrons and hydrogen has 1 electron, both in their valence shell. So I'm working with a total of 8 electrons. So HCl is going to look like this. So we've got 1, 2, 3, 4, 5, 6, and then 7, 8 electrons in the bond. So go ahead and find your periodic table and identify the electronegativity of both chlorine and a hydrogen. And so when I do that, I see that chlorine has an electronegativity of 3.0, whereas hydrogen has an electronegativity of 2.1. So I can see from this that that chlorine rather would be my slightly negative atom in this bond, and that hydrogen would be my slightly positive one. And I look at the difference here, and the difference is 0.7. And so I know that there's a dipole vector that can be created in the direction of chlorine, the more electronegative atom, and that the dipole actually has a magnitude of 0.7. And so that tells me there's a difference there of 0.7, which means that this is a polar covalent bond. And the fact that there's a net so here's my polar covalent bond, but the overall molecule is also a polar molecule because there is a net overall dipole vector here of 0.7 that doesn't cancel out with anything. So I would like to do CO2 next. So let's go ahead and draw this Lewis structure. So CO2 has, 4 valence electrons for carbon, and then 2 times 6 for oxygen. So that's 12 plus 6, which gives me 18 electrons to work with. And so I'm going to start by, putting my carbon in the middle and my oxygens on the side, and then create a bond between each of them. And so I know that, let me just do this, I've got my 6 electrons that will fill the octets of both of my carbon, or my oxygens rather, but carbon is not satisfied in this case. And so really what I need to do is I need to take the electrons in the bond and make what we call a coordinate covalent bond by moving them into the bond. And so what does that look like? I'm just going to get rid of some of this, and then we'll draw it properly. It ends up looking like this. There we go. And so investigating the electronegativities of carbon versus oxygen, take a minute to go ahead and assign carbon and oxygen their respective electronegativities. So I know that oxygen has an electronegativity of 3.5. So that's true of each oxygen. And I also know that carbon has an electronegativity of 2.5. So first of all, I need to examine that a dipole vector exists at all. And I can tell from these electronegativity differences, the difference between the carbon and the oxygen is 1.0, which puts this type of bond right here squarely in the spot of being categorized as polar covalent. So I'm going to go about assigning the oxygens, a slightly negative, in each of these cases, and I'm going to assign the carbon the slightly positive. Now this is very similar to the example we just saw above. I'm going to create a dipole vector towards my oxygen and away from carbon, and one of equal magnitude but opposite direction. So I can see here that I have a dipole vector of 1.0 and 1.0 in opposing directions. Because of that, they will cancel, and that will make this molecule a non-polar molecule that contains polar covalent bonds. There we go. Okay, I'd like to try one more example with you. All right, so let's take a look at water. So water, our two hydrogens are contributing one valence electron each, plus our oxygen. So we're working with a total of 8 valence electrons. Water is a pretty familiar molecule, so I'm going to draw it out. If you were to look up its three-dimensional structure, you would see that it looks like this. And so one might think, oh, well, if I were to draw this out, it looks like the vectors will cancel. We've already seen oxygen with its electronegativity of 3.5 and hydrogen 2.1. So at this point, I know that oxygen has the higher electronegativity in comparison to hydrogen. So I'm going to go ahead and assign them their respective dipole. And then I'm going to go ahead and I'm going to draw the dipole vector. So there's a dipole vector that essentially is going like this, and then another dipole vector going in this direction towards the oxygen. And so really, those will not cancel out. In fact, let me try to replicate this over on the side. So I've got one dipole vector going about that way, and I've got another one going sort of like that way. And so if we were to add those vectors together, I would have started here and ended up over here. So my dipole vector, my net dipole, is in the upward direction. So the net polarity of this water molecule is upward. Now that's a bit beyond where I want you to go, but I just thought you might want to understand that this molecule will not have vectors that will cancel each other out. Really, what do you need to know? This molecule is not symmetrical. Right? It is not symmetrical because, to be symmetrical, it would need to have another H sort of going up in this direction, and then it would be symmetrical about the O. But it is not. And so since it is not symmetrical, that's a pretty good cue for you to know that this molecule will not have dipole vectors that will cancel, and that this will make this molecule a polar molecule. Okay, so this is an example of a molecule with polar covalent bonds, but that overall is also a very polar molecule. So that's it for the first of our 2 lessons today. So I'm going to be assigning some homework. Make sure you look on Google Classroom and work through the homework that I've assigned. There should be a second link provided in today's Google Classroom in order to access the second of the lessons today. So hopefully if you have any struggles with this, that you will ask me on Monday, and I'll be happy to sort out any of the details that you're having difficulty with.